Good afternoon. I'm Lee Lowery. I'm with the Civil Engineering Department at Texas A&M University, and I am here tonight to go over the Strength of Materials Fundamentals of Engineering exam review with you. You have notes that we have given you. The notes are basically on strength of materials. We will be covering material that is in the Fundamentals of Engineering handbook, just so everybody knows exactly the type of stuff we're going to cover. We've been told that if the material is not in this handbook, if the equations aren't in here, then there will be no questions of that nature on the quiz. So that's where we take the information from. We also sent you a book, an EIT review manual by Lindbergh. We've taken some of the material out of that text. It's a very good text. I'd highly recommend you work as many problems as you can out of that text. All right, in strength of materials, we're looking for basic stresses in structural members due to loading, and often we also need to know the deflections. We use derived equations to get an idea of the stress level and the deflections that will be induced in that member, and then we compare those with allowed values. The type of material we'll be discussing tonight will be direct stresses. We only know of two kinds, and normal stresses and shear stresses. Normal stresses include tension and compression. Tension stresses would be, for example, in a piece of wire when you pull on it. Compressive stresses would be the type of stresses that would be in something when you press on it. And shear stresses are slightly different. Shear stresses are wiping stresses. Those are shear stresses right there. When you rub your pencil across a page and little pieces of it come off on the page. Now those stresses can arise because you do different things to a structure. You can pull on it, you can push on it, you can twist it. If you twist it, you will cause, the basic stress you cause will be shear stresses. And we'll cover each of these in detail. There are compressive and tensile stresses associated with this stress, but the basic stress is a shear stress in that rod. In bending, the basic stresses are compression and tension. Pressure vessels are subjected to tensile stresses. Then we have the case where you have combined stresses, where you may bend the structure and twist the structure and pull on the structure all at the same time. Those are called combined stresses. They're merely a combination of these previous values. And then we will study columns. Now, as opposed to stresses, we also cover deflections. Axial deflections or deformations would be if you take a bar and stretch it or compress it. Torsional deformations, when you take like a round bar, a drive shaft, and you twist it. And then beams have deflections on them when you support a load on a beam and the beam bends. I have tried to use the terminology that the Fundamentals of Engineering reference handbook that you are permitted to take into class with you, into the quiz. I've tried to use their symbols. I'll show you kind of a brief summary of what they've said, and then I want to also show you just that book again that they will let you take into the quiz, so that you'll get a feel for the material and where it's at. You definitely need to go through that reference handbook in great detail. You need to use it every time you work problems. It's not so much that you don't know the material, but it's very likely that you learn the material using different symbols than they use in the book. So be very careful about studying with the reference handbook when you work problems. All right, we talked about direct stresses. They include tension and compression, and the equation for how much stress you get in something that is stretched or squashed is you take the load and you divide by the cross-sectional area of the member, and that gives you the stress in that member. That stress can be low, it can be high. Depending on what kind of material it is, this stress should be below some set allowed value. That's how you would tell whether or not the structure is satisfactory. Shear stresses often use the same equation. They are wiping stresses. They would be, for example, cross shear on a bolt when a bolt is used in shear. When you bend a beam, you also get shear stresses in the web of the beam, stresses along the long axis of the member. Here we see an example of tension and compression. Here someone has applied a load of some magnitude on a bar, possibly a circular bar with a cross-sectional area shown. If you cut through the bar, you expose a stress inside the bar, and that stress is what actually breaks the structure. If the bar is in tension, that means someone is pulling on both ends of it. If the bar is in compression, that means it is tending to be shortened. It is being pressed on. For an example of the calculation that you might be asked to perform on a quiz, someone has a 10,000 pound load supported on a piece of steel, perhaps. The top bar has 10 square inches of steel in it, cross-sectional area, and the lower bar has 4 square inches. So the stress in that region would be, take the load, you divide by the area, and that would be 2,500, and the units for this would be pounds per square inch. If you were working in newtons, and perhaps you were working in meters, then your 2,500 would be newtons per square meter, and that's also known as a Pascal. Now, here the load was pretty easy to get. Sometimes the load, you have to really work to get the load on it. The other day we did a summary on, or a review on statics, and the entire time was spent determining these loads. The way you get this load is you cut through the section that you'd like to analyze, and when you cut through that section, you expose what the thing looks like across its area, and that area we've been told 4 square inches in this case. To find the load in section AB, you will have to cut through it, and then you look at that and you see that that area looks like this. Perhaps it doesn't look anything like the other one. There's the cross-sectional area. If you add up all of those areas on that little piece of wide flange, you'd find it has 10 square inches of cross-hatched area. Here's another example. You'll notice in this case someone is applying 8,000 pounds of load on the end of the bar. This force right here says 10,000 pounds. It's shown as a compressive force. Down here there's a force applied to this cross section. It's going to the right, and its magnitude is 5,000 pounds. So your job would be to find the stress inside of each of those sections. In order to find the stress in this first section, you have to cut through that section. Once you cut through that section, you can draw a little free body. You can put the 8 kips of load on the end. You have not cut through the next load yet, and therefore there'll have to be 8 kips of load resisting. The cross-sectional area is said to be 8 square inches. That makes it easy. So the stress in the first section is load divided by area is 1 kip per square inch, or 1,000 pounds per square inch. Now, to get the load in the second bar, you have to cut through that bar. Cutting through that bar, you see something that looks like this. It has a load on the end of 8 kips. It has a load right here of 10 kips. And therefore you have a load on this area necessary to keep that thing in equilibrium. Well, obviously this guy is beating up on this guy. 10 is bigger than 8. 8's pulling to the right. 10 is pulling to the left. The 8 needs some help, so you push enough to help. Basically, your sum of forces in the x direction is equal to 0. Obviously, then it takes 2 kips of load distributed over this area in order to keep the structure in equilibrium. It says that the stress in that section of the bar is the load, 2 kips of load divided by, how convenient, 2 square inches. Turns out the stress in the small piece is the same magnitude as the stress in the large piece, 1 kips per square inch. There is a difference. You'll notice the 8 kip load has to stretch that area. It puts that area in tension. So this stress is a tensile stress. This 2 kip load has to press against that face, and therefore this 1 KSI is a compressive stress. Then finally, you do the same thing in this last section of the bar. Looks kind of like this. Here's the bar. Here's the little piece. Here's the next piece. There's 8 kips here. This has been whacked open and is now shown as a cross-sectional area. There is a 10 kip load here. 10 kips to the left. There is a 5 kip load applied right here to the right. 5 kips. So all we got to do is find out how out of balance it is. That's how much load will go in that new cross-hatched area. Was it 13 to the right? Beats up on 10 to the left. The 10 now needs some help. The force inside the piece of steel is 3 kips worth of load. So in that area, you take the stress is 3,000 pounds divided by 6 square inches. You get a half of a KSI. The kind of stress, since the resulting force has to pull on that bar, tension. So direct stresses are usually not much trouble. Now the second kind of stress, there's only 2. They're either normal, tension or compression, or shear. Here you have a center bar being pulled out between two arms of a clevis with 1,000 pounds of load on it. The whole thing is bolted together with a 1-inch diameter bolt, and sometimes it's a little hard to see in your mind what area you're looking for. If you will take this metal bar and just yank on it so hard that it fails, then you will be able to see there is a little plug of metal that comes out with the bar, this little middle piece of the bolt right here. And if you'll take a look at that piece of metal that falls out on the floor once you yank this thing out of here, you'll see it has a nice, new, shiny, scarred up top surface, and it has another one just like it on the bottom. That is the surface area of steel that was originally holding these two pieces together. Therefore, I know the area of a circle. This circle has a 1-inch diameter, and therefore this area on the top is equal to pi d squared over 4. And there's another one just like it on the bottom. So the total area would be 2 of these. How much do you get for that?
1.57.
1.57 square inches of steel. The load is 1,000 pounds, and therefore the stress, now that's the wrong symbol for this kind of stress. The kind of stress this is a shearing stress, and you'll normally see it not listed as sigma, compression or tension, but tau. You take the load, the total load is 1,000 pounds. That 1,000 pounds had to come through this top and through this bottom surface, and it sheared this surface right here, top and bottom, 1.57 square inches of steel, and then whatever that's equal to. Now, that's not tension and not compression. That's a wiping stress. We usually care if we find out, or if the material is in tension or if it's in compression. There are some materials that fail in tension, but they don't fail in compression. They're weak in tension, but strong in compression. A piece of chalk, for instance, would be weak in tension, strong in compression. But there aren't very many materials that fail when you shear them this way. But they don't fail when you shear them this way, so we don't really much care. Shear is shear. Now here is a plug of material. It used to be inside of a plate. The plate looked like that. Someone took a die and a punch, and they actually punched this hole in the plate. And we were asked how much load did it take. Well, the equation for the stress again is load over area. I would have to go to a materials person or go to a book and find out how much shear stress this kind of metal can take. Perhaps it could take 30 kips per square inch before it failed. Then I would put that allowed value or that failure value in my equation. The stress is load over area. I was asked how much load this thing took to punch this hole in the plate. So all I really need now is the area. Well, this is the area right here. Again, you find the area the same way as you did up here. If you will take a punch, poke this thing out, let it drop on the floor, pick it up, it'll look a little bit like a dime. The top's probably all rusty, the bottom's probably all rusty, but I guarantee you this surface around this tin can part is going to be nice and shiny because it used to be holding up the load, and now it has failed. So to get this area, all you do is you multiply how far it is around that surface. That distance around would be pi d. You multiply that length of that line times how far the line moves to get from the top to the bottom. That would be how thick the piece is. In this case, the metal was, or the plate was 3/8 of an inch thick, and the diameter was given as 1 inch. and you have your area. Pi times 1 times 3/8. You stick that number right in here. Then you could solve for how hard it is to poke a hole in a piece of structural steel so that you could bolt it on the job. Alright, now, not only do structural members have stress in them, but anytime you put a load on a structural member, it deforms. It either deforms in tension, it gets longer, or it deforms by shortening, or it can actually deform in shear, where one of the surfaces slides with respect to one of the other surfaces. The equation for how much deflection you get when you load a long member is the load P is how hard you pull on the bar. Just draw one here. The load P is how hard you pull on it. Load's supposed to go right in the middle. The length of the bar is L. This is the length of the bar. The area is the cross-sectional area right across the load, across the axis of the load. And E is what they call the modulus of elasticity of the material. And those numbers are in the reference handbook. So if it says it's steel, you simply look it up in the book. Just check right quick. In your book, it's on page 32 for steel and aluminum. And so that's about the only two materials they'll be able to use on the quiz. Now, while we're at it, we might as well note the fact that deflections can also occur in a rod because you heat it, because you have a change in temperature. The equation for how long something gets if you heat it up is alpha, is what they call the coefficient of thermal expansion. Delta T is how hot the bar gets from its initial measuring, and L is how long the bar is. So for example, if you put a load P of 6 kilonewtons on a bar that is originally 2 meters long and had a cross-sectional area of 0.1 square meters, then you should be able to find the stress. And if you know what kind of material it's made out of, you should be able to find how long it gets. That symbol should be this kind of a delta, simply because that's the symbol used in the book. So change that to the other kind of delta. First, the stress in the bar would be given by load over area. Our load is 6 kilonewtons divided by the area, 0.1 square meters. So that would be 60 pascals, which is a newton per square meter. A lot of times these areas will be given in centimeters by centimeters. It's usually convenient to go ahead as soon as you can and change it all to meters. Then how long will the bar get due to that load? Let's just say it's steel. Well, how long it will get is given by this equation. The deflection is equal to the load, 6 kilonewtons, times the length, 2 meters. Let's see now, I got this wrong, don't I? That's not a pascal. It would be a kilopascal, because that's a kilonewton. A newton per square meter is a pascal. I got 10 to the third here, so I need 10 to the third here. So that's 6 kilonewtons times 2 meter, PL, over A, 0.1 square meters divided by E. So let me go over to the book on page 32. Modulus of elasticity of steel in metric units is 2.1 times 10 to the 11th newtons per square meter, which is a Pascal. And I guess before I get in trouble again here, I better change that 6 to 6,000. So I've got it in newtons, 6,000 newtons. And then whatever that works out, that would be how many meters it gets longer. You got a number for me?
5.7 times 10 to the minus 7.
5.7 times 10 to the minus 7th meters. Things usually don't get very long when you load them. Right now you're sitting in a chair. When you sat in that chair, all four legs got a little bit shorter, but not much. Alright, here's an example of temperature. This particular bar probably had an initial length of L, and it just fit nicely between two walls. Then someone heated the bar up and wanted to know how much force it caused, how hard did it push against the wall. Well, what he does to do that is he removes the wall. He pretends the wall isn't there. He heats the bar. He lets the bar go ahead now and move to the right, however far it wants to, delta due to temperature. Delta due to temperature, we know, is alpha. It's in the book, or it will be given. Delta T, the problem will have to state how much hotter the bar got, times the original length. The problem is that means the bar is where the end is where it shouldn't be. It's got stuck out further. So then it would be your job to go back to the warehouse, pick up a hydraulic jack, push on the end of that bar, and make the end of the bar go right back to where it was before it got hot. Then, holding that force on it, it would just fit between the walls again, and that's what it's supposed to do. That would be the solution for R. How short something gets, delta due to load, is PL over AE. In this case, we call the load PR, so let's put R. And since these two deformations are equal, all you'd have to say is the delta of both of them is equal to delta T, delta load, so alpha, delta T, L equals RL over AE, and solve for the force. If instead they ask you for the stress, well, right here is the stress, P over A. So you can solve for that out of that equation. Alright, now one of the tables listed in the book is a stress strain diagram for steel. They might ask you some questions about this. They may be doing nothing more than wondering if you know what E is, the slope of that line. They might ask you at what value approximately does the material go nonlinear. Yeah, it goes nonlinear around in there somewhere. Where's the yield strength? 2% yield strength. E, of course, is the slope of this line. That would be some change in stress divided by a corresponding change in strain. They also give you Hooke's law, which says stress is equal to strain times the modulus of elasticity. We assume they don't give you any of these equations without some purpose. They are loath to waste ink. So you want to know where the equations are, and you want to know how to use them. He might tell you how much stress something has in it. and he might tell you how long it got. Knowing how long it got, you have to calculate the strain. He might ask you what E is for that material. He has same equations we have. His symbols are a little different. He doesn't use delta. That's what I use right there. Delta L for him is delta line. L0 is the original length. I might mention something also. Back on this problem, a lot of people say, well, if this length right here is 2 meters, then this new length is 2.003 meters. When I put the hydraulic jack on the end, should I use 2.003 meters in there? Well, you can if you want to, but it's not going to make any difference at all. Most people just say it's 2 meters long, here, here, there, and they don't worry about that. It doesn't make enough difference to change your answer. Alright, same equation we have. You'll notice here he talks about plastic deformation, which is permanent, and elastic deformation, which is recoverable. For instance, especially on a piece of steel, which has a very well-defined yield point. If you stress something here, it'll come back down. If you load it up to here, it'll come back down. If you load it up to here, it'll come back down. If you load it up to here and over in here, it comes back down here. And that would be a plastic strain. And this is not recoverable, and that's what the notes here say. Permanent. Or the elastic deformation is recoverable. I'm not sure what this right here is for. I really figured it. Geometric compatibility is what we just did with this piece, where we made this end of the bar geometrically compatible with the wall. So perhaps that's what he's referring to, but it's in a rather strange place. He has a section on uniaxial loading and deformation. This is where you'll find the equations in the reference handbook that we just covered. Stress equals load over area, and deformation is PL over AE. Here is his version of thermal deformations. Instead of using delta T as a change in temperature, he uses T now minus T when we started, and he has the same alpha and original length. Now here's an example that you might be asked. How much does the bar elongate from one end to the other? Might also ask, how much stress is inside the bar? Let's find the loads in the bar first. Right across this cross section is 20 kips of tension. By that I mean that section of the bar is stretching, and I can guarantee you that by just hiding this piece and seeing what it takes to keep it in equilibrium. It takes 20 kips that way, tension. Now over here I can't do that. In other words, I can't cut off this end because the guy didn't tell me what this load was. He says he thinks it's compressive. Let's see. No, he did. He did tell me all the loads, so I guess... No, that's right. He didn't tell me. Here's question mark. So instead, I'm going to start on this end. As I come across here, the load is 60 kips of tension. 60 kips of tension. When I come across here, you'll notice there's 60 kips of load, somewhat balanced by 40 kips of load. The two are fighting each other, but this guy's still winning to the tune of 20, and therefore the load in this piece right here is 20 kips of tension. And now then I can come down to this section and I see 60 and 30 pushing to the left. That's a total of 70. 40 is pushing to the right. 40 isn't winning, the 70 is winning, and therefore I need in this section a force to the right to help balance the 40, and so it's 30 kips of tension. Some of those sections could be in compression and would be shortening. Some of the sections could be getting longer, and they would be stretching, getting longer. Alright, now then, what we need is we need an area for each one of these things. He told us the diameter, so the area is equal to pi times 3 squared over 4. What do you get for the area of the first one?
0.716.
0.716 square inches of... that's interesting. Oh yeah, here's his E right here. I was thinking if he doesn't tell us E, he doesn't tell us what the value is. Going to change that number?
7.07.
7.07 square inches. Alright. What do you get from our 4-inch diameter rod?
12.6.
And for a 2-inch diameter rod?
3.14.
Okay. So now then we're set to find anything else we want. The stress in bar A is load, 60 kips of tension, divided by the area, 7.07 square inches of whatever that stuff is, and it doesn't matter. We can work that out. Stress in B is 20 kips of tension, divided by its own personal area. ABC, that's interesting. It doesn't have one bar diameter there. Doesn't matter. 12.6 square inches of steel. And the stress in PC would be 30 kips of tension and divided by 3.14 square inches of steel. He hadn't told us what the last bar piece is, how big it is, but it doesn't really matter. We get it by in the same fashion. Now then, we can tell how much stretch each little piece has personally. Here's the stretch in bar A. The total stretch in bar A is equal to PL over AE, where everything deals with bar A only. So the load in bar A is 60 kips of tension. That means that bar is going to get longer. The length of that bar is 40 inches. The area of that bar we've already worked out is 7.07 square inches. And E, that's not steel. He says it's 30,000. Oh yeah, that is steel. That's 30,000 KSI. That's 30 million pounds per square inch. And this is 60K. I probably should have just left it K. That would be 60,000 pounds of load. And so this little piece of bar right here is going to stretch
0.0113.
0.113 inches of stretching. In other words, point A and point B separated by this quantity. Now then, we can do the same thing for the next section and the same thing for the next section, and if you'll give us information on bar D, I don't see it anywhere, then we'll get the same information for this section and we'll be able to tell. Some of these little guys may get longer, some of the little pieces may get closer together, not in our case because we have tension everywhere. But if they get closer together, we'll just subtract that. We'll add how far they get apart, add up all the numbers all the way down, and know where did point D go with respect to point A? All right, another kind of stress is called a shear stress. We already talked about it. This is out of a reference manual. A shear stress and a shear strain actually looks like this. You have a piece of steel, just like we had a piece of steel a minute ago, but in this case, this little block of steel has a wiping stress across its top. That has a tau stress. But what that has a tendency to do is to make this block move like that in 3 dimensions. And if you call this the length that you're going to measure, and if you call how far it moved over, say delta, then the shearing strain would equal to delta over L. And this is the shearing strain, is this angle right in here. Actually, I guess the truth is the tangent of this is this angle, but for small angles, and these are always small angles, the tangent of the angle is equal to the angle. And that's also equal to shear stress divided by what they call the shearing modulus of elasticity. And this number is also in the book. Now this equation you probably ought to watch out for, because in the book he gives you E and he gives you G for some materials. If he wants to find out if you know this equation is around and how to use it, he might instead tell you E for glass is, and I don't know what it is, say 20,000 KSI perhaps, and its Poisson's ratio is 0.41. I don't know what that is either. But you go looking for glass and you need G and you can't find it. Well, here's why. Since you have U, the Poisson's ratio, you can put it here. You can put the E he told you there, and you can solve for G. So be sure you know that equation is around and available to you. And then, of course, Poisson's ratio, here's a bar. If you calculate how long it gets, that would be a change in length divided by its original length. That would be the longitudinal strain. You'll find that bar tends to get a little bit narrower right in this section. And you can solve for the lateral strain knowing Poisson's ratio. In fact, they might ask you what the lateral strain is for a material that gave you G and gave you E. You calculate Poisson's ratio. You use this equation right here to get the answer. If you have lateral strain, now be sure you multiply it times how long this thing is, because the strain is like inches per inch or centimeters per centimeter. So if this was 10 centimeters across and you found this number right here in centimeters per centimeter, you have to multiply it by 10 to get the total necking down that it did. Alright, there's also there's that table I was telling you about on page 32, just so you kind of know what it looks like. It gives you material properties for steel and aluminum in both metric and standard units. I'm not sure he'll use that on anything. I can't think of anything real easy to use it on, but this is for 3-dimensional strains. Here are your shearing strains. Here are your normal or tension or compression strains. They are related to the stresses, and here they are defined. Just know they're there, and if it gives you something that looks like that, well, head out this way and plug it in the equations. Now, as opposed to bars that get loaded like that. We have bars that are loaded like this. They are twisted. They are torqued. The stresses induced in those bars are called torsional stresses. The equation for them is how much torque did you apply to the cross-section. That means you'll have to know how to get that torque. What is the radius of the shaft, and what is its polar moment of inertia? On page 26 of your reference manual, you'll find polar moments of inertia for various shapes. This equation is only good for circles and for pipes. It won't work for something that's square. Now, this stress is across the end of the bar. In other words, if you twist the bar says no and tries to resist with little shearing stresses across the face. They are distributed linearly. They are zero at the middle. They reach a maximum on the outside surface of the bar. Here's the bar in 3 dimensions. And on this face, you have these shearing stresses. On the bottom, of course, the shear stress will go this way. That's probably why the shearing stress is in the middle is zero, because you ask this guy which way he wants to go, and he looks up and they're going to the right. He looks down, they're going to the left. He says, "Phooey, I just won't do anything." Kind of like a volume-looking thing. And let me mention, it's really important that you know how these stresses are acting on the cross-section. There's a lot of good questions can be asked. Just where does the maximum stress occur? And you know the equation, you know it's TC over J, but you don't really know where it is or what happens. These will help a lot. You'll notice that on the surface face here, I put big arrows on the outside. That's because the shearing stresses are very large. You'll notice then the arrows start to be getting kind of small. You'll notice in the middle the arrows are tiny. For instance, out here the stress might be 2,000 psi of shear. Halfway in, they'd be 1,000 psi. And in the middle, there's no stress at all. So it's like a cone stuck in there, and this volume that remains is the representation of how intense the stresses are. Here is your reference manual's way of saying stresses. I'm not sure how he would use things like this is the twist in the theta z direction is the limit as z approaches 0 of a change in theta respect to z. Might be able to, but basically this is what you're looking for right here. You're looking for how much rotation a bar gets when you twist it. If you ask you how much rotation you get in a little tiny short piece, I guess that would be good. And this, of course, is nothing but this same equation. It gives how much twisting moment per radian of twist there is. He also gives you the equation for a hollow thin-walled shaft. So, for example, if you had a very, very thin, hollow, thin-wall shaft, you can say that the shearing stress is, take the applied torque divided by this area, where that area is the mean area enclosed by the shaft measured to the midpoint of the wall times how thick is the wall. If you would rather, you can just use the same equations you had before. you can just say that the stress is equal to the applied torque times the center to the radius to the outside surface from the center, and you divide by J. For a thin piece, you'd have an R inner, you'd have an R outer, and the J would be pi times R outer to the fourth minus R inner to the fourth divided by 2. And then you don't need to know any special equations, and you don't have to measure to the middle of this when you measure this area. And it's just probably just as easy to do it that way. All right. Now, in order to use these equations, you have to be able to get the torques inside of these sections. We do the same thing we've done before. In order to find out how much torque is in this shaft, you must cut this shaft. You come around this end right here, and you isolate nothing but what you see in that free body, and the answer for the torque in this section is 500 inch-pounds. Inside of there, it is tending to do this to the shaft. It's tending to go this way on that end and this way on that end of this shaft, because I can see it's going kind of clockwise on the right-hand end. To find out how much torque is in this section, I do exactly the same thing. I simply cut it out. Now I see that 1500 plus 500 are both getting together, causing me grief right here. The torque in here is 2,000 inch-pounds of torque. Then I come to this section right here. Here's 500 clockwise, 500 clockwise, total of 2,000 minus 2,000. There isn't any torque in that part of the shaft. You might say, well, why did we buy it? What's it doing there? Well, right now there's no torque in there. The loads may change. Somebody may take some more power off of this thing sometime later, but right now there's no torque in here. I come back to here, plus 1,500, plus 1,500, minus 2,000, plus 200. The torque inside of there is 200, and the torque inside of there is tending to do this to that end and this to the other end. After a while it gets old, it'll probably be shorter to change and go the other way, and the final torque right in here has to be 1,000, because that's what's in that free body. You can check it. Plus 5 plus 15, that's plus 2, minus 2, that's 0, plus 2 plus 8, that's 1,000. That's correct. This guy says this is what he's doing to that shaft. He says, I'm doing this to that shaft. Looking at this free body, this guy says he's doing this to that shaft. You'll notice both of the people agree to what we're doing with that shaft. This guy says going this way, therefore this is the resisting. This 800 and 200 say we're going this way, and that's the resisting. They both agree. Alright, here's another one. Sometimes you'll see the notation, a double-headed arrow, which merely means right-hand rule. That's what he's talking about here. Point your finger the direction the two arrows go. Your right hand tells you which way this is being twisted. Answer for the torque in there, 4. Answer for the torque in here, 8. 4 minus 12. Answer in the torque in here, 4 plus 2 minus 12, there's 6. And you should be able to figure out which way they're going. Alright, now this is how much a shaft will deform when you put this load on it. The total, this probably ought to say total rotation between any 2 points on a shaft. The answer comes out in radians. T is the applied torque, L is the length of the shaft, G is the shear modulus of elasticity from your reference manual, J is the polar moment of inertia. You don't have to memorize that equation. It's in the reference manual. This just shows what we're talking about. If you have a torque on this end, you have to have an equal and opposite torque on the other end. The amount of phi angle would be how far it is from here to here in radians, how much that shaft wraps up. So for example, if the torque was 20-inch kips, if the material was steel, modulus of shear for steel 12 times 10 to the 6th, 10 to the 3rd kips per square inch. If the length of the shaft was 10 inches, if the size of the shaft was 1/2 of an inch in diameter, then we could tell how much it twists. Total amount of twist would be equal to T times L divided by G divided by J. J is pi over 2. Since this bar is solid, it would be times the radius to the 4th power. And no matter what it comes out, whatever it comes out, that's how much rotation you'll find in radians. If the answer on the exam, if you got 4 or 5 answers on the exam and they all say 2 degrees, 8 degrees, 17 degrees, then you'd have to multiply that times 360 divided by 2 pi. That's a complete circle. That's a complete circle. Now, bending stresses. The nice thing about axial stresses is I can show you or remind you how they work very quickly. Torsional stresses, well, torsional stresses take a little more time. Bending stresses really take more time than anything. The reason is the equation for how much bending stress you get in a beam is MC over I. In order to get M, you have to be able to find or to draw a shear and a moment diagram. In order to get C, you must know how to find the centroidal location of a beam. And then in order to get the moment of inertia, you have to be able to get the moment of inertia about that centroid for the beam. So it's no question a more complex operation. The bending stresses are given by MC over I. M is how hard you bend it, the applied moment. C is the distance from the neutral axis to an outside fiber on the beam. I is the moment of inertia of the beam. This should say about the neutral axis, about the centroid. Now, the reason you need to emphasize that is a lot of the ME profs showed you how to get the moment of inertia about the base. It has one, but it just doesn't bend about that line. It always bends about the centroid. These stresses will be tensile or compressive, and there's 0 at the neutral axis and a maximum on the outside fibers. This is how they look. This is the distance C. Here's your neutral axis. Here are your stresses on the outside fiber. You'll notice that they are biggest on the outside fiber. This particular beam is being bent like that. And the reason I know is because these little arrows are banging into this surface, causing compression arrows on the top, causing stretching or tensile arrows, stresses on the bottom. You need a sign convention and your reference manual and many books decide to use this as the sign convention for positive bending moments, and this is for negative bending moments. So if your beam is bent into a smile, it's got positive moments on the ends. If it's bent into a frown, it's a negative bending. You can check a sign convention by looking in the reference manual. Positive and negative shear, if one side tends to go up and this side tends to go down, that would be positive shear. There is a relationship between load, shear, and moment. And all you got to do is you integrate the load, you get the shear, you get the change in shear. You integrate the shear, you get the change in moment. We'll show you how to use that in a minute. Now, back to being able to find the centroid of a piece. We discussed this in the static section, but just to refresh your memory, you should draw a reference axis at the base of the figure. Incidentally, this is the end view. Draw the beam, it's going back into the board. You draw an end view of the beam, and that's where you get your moment of inertia, and that's where you get your centroid. This particular one is 100 centimeters across and 20 deep, and this is 100 by 20. Somewhere around in here is the centroid, that far from the reference axis. In order to solve for it, you'll have to break this up into two areas that you fully understand, Area 1 and Area 2. I fully understand rectangles. Here is the centroid of that rectangle. I fully understand this rectangle. There's the centroid of that rectangle. This is that far from the reference axis. Half of 100 is 50. This one up here is that far, which is 110. So I should be able to find Y bar. Y bar is equal to, you selected the top piece as Area 1. It's 100 centimeters times 20 centimeters times how far is it up in the air from the reference? It's 110 centimeters. Plus, here's Area 2. It's 20 centimeters by 100 centimeters. It happens to be 50 centimeters up in the air. Divided by Area 1 plus Area 2. Area 1 is 100 times 20, plus Area 2 is 20 times 100. Well, if you can give me a number for that. While you're calculating that, I'm going to put neutral axis here. That is the neutral axis. Everything above that point will go into compression when it's bent. Everything below that point will go into tension, unless the moment is in the other direction, in which case those would be reversed.
80.
Oh, you're kidding. 80? Right on the money? Amazing. Alright, now then, so this neutral axis is 80 meters off of the reference, 80 centimeters off of the reference axis up in the air. Now, everything, all areas have a moment of inertia just because they're there. All they got to do is just be. They get a moment of inertia.
The list of the magnitudes of those moments of inertia in your reference manual are on page 25, 26, around in there. Now, they will give you moments of inertia about some rather strange axes, but the only ones you really need when you talk about bending of beams is I about the centroid, and that'll be shown in the book as I sub xc. So, this particular piece has several moments of inertia. First, there is a moment of inertia due to area 1 about the centroid of area 1's own personal centroid. That's listed on page 25. It is listed as the base of the item times the height of the item cubed divided by 12. If it was a triangle, it would be base times height cubed over 36. So you got to look and see what the moment of inertia of the piece, just because he's alive, how much that is. So in our case, just because area 1 is there, he has a base of 100, he has a height of 20, cubed divided by 12. That's how much moment of inertia the top piece has just because he's there. Got a number on that one?
66,667.
Alright. Now there is a moment of inertia of area 2 just because he's there. It is also a rectangle, so it will be a BH cubed over 12 item. His base, and incidentally the base is the horizontal dimension, his base is 20 centimeters times his height, which is 100 centimeters, cubed divided by 12. This might have been a good reason to put this in meters, but neither meters nor millimeters work out with very nice numbers. What do you got?
1666667.
Alright. Centimeters to the 4th. Now, if you nail these two pieces together, if you glue them together, if you bubble gum them together, and they don't move relative to each other when they're bent, then they become one piece, and you pick up an extra moment of inertia. If, on the other hand, you just lay this on top of that, you're through. That's all the moment of inertia you get. They both, in effect, they both bend separately. But because we're going to glue these together or nail them together, you get, because area 1 is there, a transfer moment of inertia. And that transfer moment of inertia is how much area 1 has multiplied times how far is it from the neutral axis, D, from the centroid of the piece to the neutral axis. And you don't only get that, but you get it squared, AD squared. Alright, in our case, area 1 is a 100 by 20 piece, and its distance to the centroid is how far it is from here to here. In other words, that's how far area 1 is away from the neutral axis. Well, this was 110, so 110 take away 80 is 25. So that's how many centimeters it is to area 2 centroid from the neutral axis. So we multiply that times 25 squared, and that's the transfer moment of inertia. You also have a transfer moment of inertia for area 2. He is 20 wide by 100 deep. What'd you get for this one?
180 000 000
Wait a minute. 1800000.
000.
You sure now? Count them rascals.
6 zeros.
1, 2, 3, 4, 5, 6. All right, so that's 18 million. Now the question is, how far is it from here to here? That's the distance area 2 is away from the neutral axis. Well, this was 80. The centroid was 50, so he is 30 centimeters away. So we have 30 squared. What do you get for that?
It's the same.
Is it the same? Can't be. Maybe I got it wrong. I think you're right. 20. The top one is 30? Thank you. I counted wrong. Let's go back and see why. The reason he knows they should be the same is because this area on top is the same as this area in the middle, and therefore the neutral axis ought to be dead between the two of them. So he knew something was wrong there. It is 110 to this point here, and take away 80, well, that in 25. That's what the banker said when I tried to give him $25. He said, no. All right, so 30 squared. So that was you gave me the right number. You thought maybe nobody'd notice, huh? All right. And then all you do is you add them all up. They'll always be positive unless the area is a hole, like a missing piece. So if somebody gave you this, and you would draw a reference axis, you would take area 1 as a positive area, then you take this hole as a minus area, and you'd solve for where the centroid is. When you did the moments of inertia of each piece by himself, this would be a positive area, and therefore a positive moment of inertia. This guy would contribute a negative. Incidentally, if that was a circle, the moment of inertia is listed, pi radius to the 4th over 4. Then the transfer moments of inertia, this guy's transfer moment of inertia would be positive. See, his d there is going to be squared anyway, so it doesn't matter if he's below or above. And this guy's transfer moment of inertia would be negative because he's a missing piece. Alright, sometimes they'll give you a channel on top of a wide flange. And they'll go ahead and tell you that this wide flange is 30.94 inches deep. And they'll tell you how far it is to the centroid of the channel. And they'll look in a book and they'll say the wide flange is a 30 by 211, which has this many square inches of area and has this moment of inertia about his own personal centroid. The channel is a 15 by 50. He has this much area, and he has this much moment of inertia about his own personal centroid. We intend to weld these two pieces together, locate the centroid, and locate the moment of inertia about that axis. You'd work it exactly like you did any of the rest of them, because now you know what this area is. That's all that's ever required, regardless of how strange it looks. You know its cross-sectional area, and you know this one's cross-sectional area, and you know where it lives, you know where its centroid is, and you know where that one's centroid is. So you simply flop it in the equation. Y bar is equal to A1Y1 plus A2Y2 divided by A1 plus A2, and that'll tell you where the centroid is. Once you know Y bar, you'll be able to find out how far that guy is away from the neutral axis, and you'll be able to find out how far this guy is away from the neutral axis. This one would be called D1, this one would be called D2, and you simply plug in the same equation. You'll work out 4 moments of inertia. Two of them you're already given. You're already given this guy's own personal moment of inertia. You're already given this guy's own personal. All you have to do is then calculate the AD squared for area 1, the area D squared for area 2, and add them all 4 up. You might try that for practice. Alright, sometimes I'll give you something that looks a little strange, ask you where the centroid is, where the moment of inertia, or what the moment of inertia is. Works just like all the rest. This doesn't look too good. This is supposed to be just one solid piece. And these also, computer didn't grade this shading very well. You solve it like always. You draw a reference axis at the base, and you discuss only areas that you fully understand. Here's one way you could split it up. You could split this up into a triangle, because I fully know the area of the triangle, and I know its centroid is 1/3 of the way up. That would leave me a rectangle here, and I know its area and I know its centroid. I could leave this rectangle up here alone, and then finally I'd have another triangle with those centroids. I could say area 1 times distance 1 plus area 2 times y2 plus area 3 times y3 plus area 4 times y4, and I have the answer. You could also pretend that area 1 is a solid piece. The whole thing is solid. And then you subtract this and you subtract this. You make these two minuses in all respects. You put them as minus areas in your centroid equation. You put them as minus moments of inertia about their own axis. You put them as minus moments of inertia for their transfers. That way you'd only have 3 terms instead of 1, 2, 3, 4 terms. Sometimes that's very handy. For example, anybody asks you the moment of inertia of this, of a box, don't break it up into all kinds of little pieces. Its centroid is dead in the middle due to symmetry, and its moment of inertia is equal to this square right here. That would be a BH cubed over 12 for the outside square. This doesn't have an O on it, it's just 12. Minus B inner, height inner, cubed over 12, because it's a missing piece. Its centroid is also right on the top. Neither of them have any transfer moment of inertia, because they live right on top of the neutral axis, and therefore this is the answer. Alright, so we've discussed how to get the centroid, how to get the moment of inertia about the neutral axis. Now we'll determine how to get the number m in the equation. MC over I. To do that, you must be able to draw shear and bending moment diagrams. You will use statics to solve for reactions on the beams. The area under any diagram will give you how much the next value changes on the next diagram. You can integrate it, but that's basically what integration says. The area under any curve between any 2 points tells you how much the next value changes from its original value as you move across the beam. You can also, from the calculus, find that the magnitude on any diagram, how high it is on that diagram, tell you how slopey the next diagram is, gives you the slope. Also, if a load is a constant uniform value, then I'll just write this down for right now. We'll get into it in a minute. Where the diagram crosses the x-axis will be found by taking the starting shear and divide by the load rate. That's also from the calculus. And don't expect you to understand it right now, but just so you'll remember. Alright, here's the beam. And that beam has 15 kilonewtons per meter load on it for 2 meters. And I've been asked to draw a shear and a moment diagram. The reason for solving for the shear diagram is so I can solve for the maximum shear in the beam. The reason I do a bending moment diagram is so I can find the biggest bending stress in the beam. Now then, I won't bore you with solving for the reactions. This reaction was 20 kilonewtons. This right-hand reaction was 10 kilonewtons. We learned how to do that in the statics section. You are supposed to simply do what the loads tell you to do. And they will tell you in great detail what to do. You should take your pencil on the left-hand side of the beam out in the air. You ought to start dragging it across. And as a load says do something, you do what it tells you to do. This load, when I cross it, says go up 20. And therefore, that's what this diagram does. It goes up in the air 20 higher than it used to be. Since it always starts at 0 on the left-hand end, then it's now 20 kilonewtons in the air. As you drag your pencil across here, there is nobody saying to go up or down, and so you don't go up and you don't go down. You simply drag your pencil horizontally across the page. Now you'll notice this was a concentrated jump in the value because this was a concentrated load. When you moved 1 millimeter, when you moved 1 angstrom, you had already crossed the full 20, so you had to go bang up in the air, 20. Now these loads, on the other hand, are not concentrated loads. These loads you would have to move a whole meter before you would pick up 15 kilonewtons of load. It's like sugar bags stacked across the beam. And therefore this load doesn't say go down 15, go down 15, go down 15. He says start here, and as you move 1 meter, you will cross an area, and that area will tell you how much to go down. Well, the amount we go down is 15 kilonewtons every time we move 1 meter. Well, this looks like about 1 meter right here. So as we go 1 meter from here to here, we are supposed to be 15 kilonewtons lower than we used to be. We used to be at 20, so that means we're now at 5 kilonewtons. You'll notice as we move another meter, he tells us to drop another 15. We're now 5 above the line. If we drop another 15 by the time we hit this horizontal point, then we'll be 10 kilonewtons below the line. And that's what this thing shows. As you drag across this on the beam, there are no loads saying go up, there's no loads saying go down, and therefore nothing happens. This point looks like it's going to be a straight line, and if you went every 1/10 of a meter, you'd find it would be. Alright, now a mathematician said, you notice how you got this point, you got that point, got that point, got that point, got that point, got that point? And I said, well, yeah, I needed those points, so I knew what the line looked like. I'm getting ready to use the areas under these curves to draw the next curve. He says, well, you know, there's a lot easier way. Why don't you just plot this point and then just plot this point here? I said, well, then I wouldn't know what the line looked like. It might be a parabola. He says, no, straight horizontal lines, if you integrate them one time, that's like a constant. And if you integrate a constant, you get like a power of x, x to the 1 power, and that's a straight line. So anytime you see a straight line on a diagram, you can be pretty much guaranteed you're going to have a straight sloping line on the next diagram. He says not only that, that works here too. If you integrate a nothing, it turns into a constant. So if you ever see a region of the beam with no load, you'll see this is a straight horizontal line. If you see this as a constant, you'll see this is a straight sloping line. If the little arrows are pointing down, then the little line ought to be shooting down. That works here too. Straight horizontal line turns into straight sloping line. Straight sloping line turns into a parabola. Alright, we were going along, we were at 10. As we crossed the beam, nothing happened, so we stayed at the same height. All of a sudden, we bump across this 10K load pointing up. Boom. Moment diagram closes on 0. That's pretty nice. Now, the next thing I'm going to do is I have used this area and this area and this area to draw this next diagram, which is a shear diagram. Now I'm going to do the same thing to draw this moment diagram. This moment diagram, this shear diagram has an area as you go from point A to point B. As you go from A to B, you cross a half of a meter, 0.5 meters, times 20 kilonewtons tall, so that would be 10 kilonewton meters. So as you go from A to B, you cross a positive area. You don't have little arrows telling you which way things go now. You just have to say above the line is a positive. And you cross 10 kilonewton meters, and therefore I put a 10 kilonewton meter spot on the page. When I want to know what the line looks like, straight horizontal lines turn into straight sloping lines. Now actually on this quiz you probably, well, I don't know, because he could ask you which moment diagram is right, you know, and not put any numbers at all. So you really ought to know what the shape of these things look like. All right, now the question is if you're going to call this thing here area 2, we're going to have to get its area somehow. And in order to get its area, we're going to have to be able to get its base. And that's what the mathematician told me. This is what you would call X bar, where this guy who starts right here, where does he cross the axis? What is the base? The mathematician says from the calculus, X bar is take how high the shear is and divide it by the load rate. That load rate will have to be a constant or you wouldn't be able to divide by it. It wouldn't make any sense. But our load is constant. So to find X bar, I go and find the starting shear. That number is 20 kilonewtons. And I divide it by the load rate, which is 15 kilonewtons per meter. Kilonewtons cancels kilonewtons, meter goes upstairs. Even the units are right. That is 1.33, thank you, meters. So the base of area 2 is 1.33 meters. Now I calculate how much area 2 is. Area 2 is a triangle, so that's 1/2 base times height. That's 1/2 of 1.333 meters. The height is 20 kilonewtons, is equal to 13.3 kilonewton meters. So that's what this guy says. As you cross area 2, you cross a positive area. That area pushes the next diagram up. How much does it push it up higher than I used to be? Whatever the area is. I used to be at 10. I add 13.3 to it, and I note that the peak is at 23.3 kilonewton meters. Now, on the quiz, you won't care what the curve looks like because he can't hardly ask you that. But if he asks you, in other words, he might not give you numbers. He might just say, which moment diagram looks the best? So here's a moment diagram, maybe looks like that. If you don't know which one is right, well, you don't get the points. And he gives you 3 other choices to boot. So it's pretty easy to get what this parabola looks like, since this is a straight line. This is an x to the 1 power curve. Once you integrate an x to the 1 power curve, you get an x to the 2 power curve. That's a parabola. Either this parabola is right or this parabola is right. Now you can find out which one back from the calculus. The calculus says that the value on any diagram tells you the angle of the next diagram. So what you do is you look right here and you see this value. Well, this value is 0. Therefore, the next curve should have a slope of 0. And that means this parabola is not the right one. This is the right parabola. Alright, finally, we now need this area 3. We would calculate the area of a triangle, subtract that area, that would put us here. Then we finally calculate this area 4, subtract that area, because it's below the line, it's a negative area. The moment diagram should close on 0. If he asks us for the maximum moment, here it is. Asks us, in fact, I wouldn't do any more work on this one. If he asked me for the maximum moment, see this area? It's going to push the diagram up. See this positive area? Going to push this diagram up. See this negative area? Going to push this next diagram down. See this next one? Going to push this diagram down. Well, fully, I found the max. I'd take it. Alright, here's one with a concentrated moment on it. I won't do the whole thing. I will say this reaction here is 450, because I see that's what the shear is. And this reaction here is 1350. Can solve for that from statics. But suffice to say, let's just take a look at the shape of the diagram. As you go across point A, you cross a 450 instantaneous push-it-up arrowhead. So you push it up 450. As you go from A to B, you cross no load, and therefore you don't do anything. As you go from B to C, you can't go any further because there's a guy here who wants you to do something special. So you'll cover only this much of the load. That area will be 300 tall by 3 meters wide. That'll be 900 negative pointing down. You'll notice if you're at 450 now, you're at 450 below, that's 900, so you'll put this point just to the left of point C. In order to know what curve to connect it with, straight horizontal lines turn into straight sloping lines. At that time, you can only go 1 millimeter because a concentrated load is there. He says, I want you to instantly go 1350 higher than you used to be. You drive your pencil 1350 higher than you used to be. If you go 1,350 feet out of a 450-foot hole, you end up 900 above the line. Then finally, you cross this area here, which is 300 times 3, that's another 900. That closes. You'll notice that even when you cross this concentrated moment, that does not change, it does not show up on the shear diagram. The reason is this is not a pointing up arrowhead, it's not a pointing down arrowhead, This thing here keeps track of only things that point up and down. Shear. Now then, as you go from A to B, you cross an area, and it is driving the diagram up in the air. As you go from B to B prime, you cross a positive area, it's driving the diagram up in the air. As you go from B prime to C, you cross a negative area, which pushes the curve down a little. As you cross this triangle, it's a big old area, it pushes the diagram way on up. Might look like that, might look like that. Let's see which one. Here is the zero value. Here is the zero slope. That's wrong. This is not a zero slope on this end. Ask any skier, he'll tell you that's not a zero slope. That's a zero slope. Problem is I end up in the air. It didn't close on zero. It's pretty obvious what I need to do. I'm 27 in the air. This is a concentrated moment. Now that concentrated moment says, boom, go down 2,700. Now sometimes you may wonder, well, how do I know to go down? How do I know not to go up? Maybe you don't want to go up. You just made matters worse. If you ever find your 2,700 off, look around for a concentrated moment. Maybe that's why it's off. You need to take that concentrated moment into effect. Alright, now let's put all this together. Here I have a beam, has a reaction on it of 2,000 pounds, and a reaction on this end of 3,000 pounds. Whoops, that's wrong. That's 3,000. This is 5,500 here. And I'm just stealing that. I'm cheating from the shear diagram, because we know how to get reactions. This 5,500 pound reaction and 3,000 pound reaction support these two loads. He draws the shear moment diagram. The load comes down 2,000, he drops 2,000. No loads, no change in magnitude. Up 5,500, 2,500. No loads, no change. Drop 5,500, no load, close on zero. This is a negative area, that's a positive area, this is a negative area. This is 2,000 times 3. 2,000 times 3 is 6,000, that's what he's got. Down to 6,000. This is 2,500 times 6. That drives it up to 9,000. 3 times 3 is 9, closes on 0. So he's got a moment diagram, got a shear diagram. Now he has been asked to solve for the bending stress in this beam. This is an end view of the beam. This thing on the top is a 6 inches. This height here is a 2 inches. This is a 6 inches. He's already solved for the centroid by drawing a reference axis. The centroid turns out to be 5 inches from the base. And he wants to find the bending stress in the beam. Alright, in order to do that, he'll have to find the centroid of the beam, and he'll have to find the moment of inertia of the beam. Let's just check his numbers there. His beam is 2 inches by 6 inches. It's connected to a 2 inch by 6 inch piece. Since those are both the same, the centroid is going to end up right in the middle, dead between these two. That's what we found a minute ago. But we'll solve for it anyway. Here's our reference axis. This is Y bar. Y bar is equal to A1 is up on the top. Area 1 is 7 inches from the reference axis, plus a 2x6 item 3 inches up from the reference axis divided by, just write these areas down again, is equal to, and did you get a number 5? Thank you. Oh, and we knew the number because he told us it was 5, so that agrees. Now he has not told us the moment of inertia, so we'll calculate the moment of inertia. First, we get a moment of inertia for the top piece about his own x-axis. Just because he's here, he has a moment of inertia about his own personal x-axis. You look in your reference manual, that would be given by bh cubed over 12. His base is 6 inches. His height is 2 inches. Cubed divided by 12. What is that? 4. He has a moment of inertia for area 2, just about his own personal x-axis. Its base times his height cubed divided by 12. What's that?
36.
36. 12 times 12 is 144.
6.
Oh, is this wrong? Oh, it's only 6 inches deep. Thank you. Alright. 36. Now then, he has a moment of inertia transfer for area 1. Area 1, if area 1 lived right on the neutral axis, he wouldn't get any transfer, but because he's off the neutral axis, he gets a transfer. He's 6 inches wide, 2 inches deep, and here's how far he lives off of the neutral axis. This is 1 inch, this is 5 inches, and that's 6 inches, so that's 1 inch, so it looks to me like he lives 2 inches off the neutral axis. Don't forget to square AD squared. One of the answers on the quiz probably will be with a moment of inertia AD. What do you get for that?
48.
48. And finally, area 2 has a transfer. And it's going to be the same in this case because both areas are the same and they're both the same distance. If you work it out, you get 48. This thing has a moment of inertia equal to how much? 4 plus 36 plus 48 plus 48.
136.
136 inches to the 4th. Alright, let's go back to the problem. Notice that's what he got also. The equation for bending stress is MC over I. In our case, the maximum bending moment was 9,000. In that case, it was foot-pounds. We got our moments of inertia in inches, so let's multiply that times 12 inches in a foot times C. Well, there's 2 C distances. We can either find the stress down here or we can find the stress up here. If you were asked for the stress on the top, you would use how far it is from the neutral axis to the outer fiber equal to 3. If you want the stress on the bottom, you'd use a C is equal to 5. If you're asking for the biggest stress, you would go to the bottom and use the number 5. In this case, he wanted the maximum stress, so he uses 5 inches. He divides by the moment of inertia of 136 inches to the 4th, and he gets 3,970 psi. Now, he also says tension. Now, good point. If you remember, we said anybody who was bent like this was a positive bending moment, bent in the shape of a smile. Since this region has positive bending in it, then this piece right here must be bent in the shape of a smile. That means the top fibers have to be squashed because they're mashed closer together. You can tell these bottom fibers have to be stretched further apart. And therefore, in regions of positive bending moment, the moments above the line, you have compression on the top fibers, you have tension on the bottom fibers. So when he went to the bottom fiber, he was finding a tension stress. That's why he puts tension for that stress. It'll be very important you're able to do that. I think it'll be very likely they'll ask you whether it's a tension stress or a compressive stress. All right, in this region, there's tension on the outside. There's always compression between the line and the moment diagram. So you can just put little C's inside, put little compressions inside between the line, between the zero line and the moment diagram. Now to find the compressive stress, here's his equation for compressive stress. Put 6,000. You'll notice he put 6,000 right here. Oops. That's interesting. He must be looking at this point for compressive stress. See, the interesting thing is sigma is equal to MC over I has two sets of numbers in it. If you go looking for the maximum compressive stress at the 9,000 spot, at this spot right here, you are forced to use the fibers to the top of the beam, and those fibers, they're only 3 inches up there. So let's just do that. If you decide to look for the moment at the 9,000 foot-pound mark times 12 inches in a foot, you'll be forced to use the 3-inch C distance because that's how far the fibers are up in the compression range. You must go to the compression side. Then you divide by 136 inches to the 4th power, and you find the true compressive stress on the top of the beam at that point. How much?
2382.
2382. Now what he noticed was, maybe I should look at the point where the moment is smaller. Gee, the moment's smaller. I can't imagine the stress is going to be smaller, but let's check. So he tries the 6,000 moment location. He multiplies times 12 inches in a foot. He multiplies times 5 inches now. The reason being is in this region, the compression fibers are on the bottom, so he gets to go 5 inches from the neutral axis to the bottom fiber, divided by the moment of inertia is 136, and now he gets 2650. And this is the winner for the compressive stress, even though it is at a place that doesn't at first appear likely to have maximum stresses because we don't have the biggest moment there. Very tricky. All right. Now here is the manual's equations. Say the same thing we said before. This is the strain instead of stress. If you wanted stress, you might just go ahead and use your stress equation and then turn it to strain using the relationship between stress and strain. Here is your MC over I equation. MC over I. You may not want to go all the way to the outside fiber and find the biggest stress. If they ask you to find the stress 2 inches up, well then you'd put a 2 here, even though that may not be the maximum stress. He may say, look, I don't want the maximum stress. I want to know what the stress is 2 inches above the neutral axis. Then you put a 2. Now, the section modulus is defined as I over C. This lets you design beams. He could give you some beam tables, but I think it's a little unlikely. But still, he might ask you something else about a section modulus, so you should know what it is. Where that came from is people were putting the known allowed stress here in the stress slot, and they were putting the moment that they knew had to be carried here, but since they didn't have the beam yet, they didn't know the distance from the neutral axis to the outer fiber on the wide flange, and they also didn't know its moment of inertia. So they rewrote the equation and said sigma is equal to m divided by I over c. Then they asked the guy who made the beams, tell me I, yeah, tell me c, yeah, but for every beam you have in the book, divide that number out for me. And so the guy who makes those beams divided I over c and called it a section modulus. That meant that a designer could then rearrange this equation and say S is equal to m over sigma. This would give him the required section modulus is equal to the m from the moment diagram, and he would divide it by the allowed bending stress. Knowing this and knowing this, he'd get something like 60 cubic inches, and he would go in a book and he'd find the lightest book that had that much section modulus, and that's the one he would use. Alright, now every beam has not only bending stresses in it, but it also has cross-shearing stresses in it. And those stresses come from the following. Showed you in a beam, let's just say it's a rectangular beam, showed you that that beam will normally have compressive stresses on one side of the beam, and they'll have tension stresses on the other side of the beam, and they are distributed linearly from the neutral axis. They are maximum on the outside fiber. They're zero at the neutral axis. Now what happens is, on most beams, if you cut out a little slice, the moment on this end is not necessarily the same as the moment on this end. Now, if the moment on this end is a little moment, and the moment on that end is a big moment, then the stresses on this side will not be as big, since the moment that caused those stresses is not as big. And that's okay. As you noticed earlier, many times the moment diagram changes value as you move across the beam. The interesting point comes from a guy who cuts this for a free body. Let me show you these stresses. So this is the tension side, the compression side. The guy one day was cutting a free body around here like this, and he only went up halfway up the beam, and he cut through the middle of the beam, kind of like that. And we all watched him do it. There's nothing wrong with it. You can draw any free body you want to. It's perfectly legal. And he drew the bottom half of the beam, and this is what he saw. On this side, he saw some really big stresses. See, this is A, B, C, D. This is A, B, C, D. This is only a half a beam. He saw a triangle there which was pulling like crazy. On this side, he saw a little weenie pulling like that. And he says, that little piece is not in equilibrium. And we said, well, wait a minute. Maybe there's some stresses out in here. He says, I don't think so. So there's nothing in there but air. Nothing on the bottom but air. Nothing on the back side but air. The only way this force here can be resisted is if you have some shearing stresses like this. And that's where those shearing stresses come from. Now, I'm not going to derive that, although it's easy enough to do. But the equation for those shearing stresses is VQ over IB. That's also in your book. Where the shear V comes from your shear diagram that you drew. If you want to know where the biggest shear occurs in the beam, probably a good bet to go where you get the biggest shear on your shear diagram. Q is a little strange. I'll show you how to do that. Moment of inertia, you know what that is. You'll notice this is the only one that's worth any money. It's a moment of inertia about the neutral axis. Don't ever find one about any other axis unless some mathematician just asks you to do that for fun. And finally, how thick is the beam where you want the stress? Okay, we're about to run out of tape here, so we are going to go ahead and change to the next tape.